Percent yield is the next concept we'll discuss. This is directly related to stoichiometry. Now, we will do some practice with stoichiometry. You will have some sheets actually while I am away. But in the meantime, I just wanted you to have an understanding of what percent yield is, and then we'll also move on to limiting reactants. Both of those are in the CK12 assignment that is coming up due soon. For every stoichiometry problem, we will have a theoretical yield, which is the maximum amount of product that can be produced with a given amount of reactants. Now, what you need to understand is the theoretical yield is in a perfect world scenario. Every particle of reactant will find every particle of the other reactant and will transform into the product that you have desired. While theoretical yield can occur in reality, it's not very common. To get every single molecule to react generally takes a lot more conditions to be much more perfect than they actually are in real life. What we do really focus on in the real world is an actual yield. So this is kind of like what we did with the percent errors. Very similar because you have an accepted value, which would be more like your theoretical yield, and they have an experimental value, which would be more like your actual yield. The actual yield is the amount of product produced when the reaction is actually carried out in a laboratory. Now, in some situations, the difference is very small, only a matter of a couple of tenths or hundredths or thousandths of a gram, but if you remember how big a mole is, that's still a very substantial number of molecules or atoms or formula units that are not reacting as expected. So as for why an actual yield might not equal the theoretical yield, there are several reasons, but really we can't expect every single reactant to turn into the product that we expect it to turn into. There are just all sorts of factors that would prevent every single molecule or every single formula unit or atom from turning into the product that we would expect. Among them, just spatial considerations. If you have one molecule or particle of reactant that's very far away from another molecule or reactant, they just may not come in contact with each other. That's one of the main issues for why an actual yield would not be equal to a theoretical yield. Now, very much like the percent error calculation we did earlier, percent yield is your actual yield divided by the theoretical yield times 100. In nearly all cases, in fact, in all cases, you would expect the actual yield to be less than your theoretical yield. Theoretical yield is the maximum amount of product, as it says up here. The maximum amount of product is your theoretical yield. So you would expect to have some number that's less than your maximum amount as your actual yield. Now I see I have some animations that I need to fix here at the bottom, but just to take a look at this problem, we have in every single stoichiometry problem, we have to look at what our knowns are. So in this case, 45.8 grams of potassium carbonate. By now you should be able to say what potassium carbonate is without having to worry about charges or what carbonate is or what the symbol for potassium is. By now we should be familiar with those things. But 45.8 grams of potassium carbonate are reacted with an excess of hydrochloric acid, which means we have more hydrochloric acid than we possibly need. And we produce 46.3 grams of potassium chloride, along with water and carbon dioxide. First, we would need to calculate the theoretical yield, and then we would use that to determine the percent yield of potassium chloride. Now, the steps here are very much the same as stoichiometry. So step one, we have our balanced equation. It mentioned here potassium carbonate reacting with hydrochloric acid to produce potassium chloride, water, and carbon dioxide. So to calculate the theoretical yield, and we'll use that then to calculate the percent yield of potassium chloride. So the first step is the same for every other stoichiometry problem that we've seen, a balanced equation. Second will be to convert your grams to moles in this case, or units to moles, whatever those units happen to be. In this case, We want grams. This is the gram molar mass of potassium carbonate. Our grams will cancel out. We're left with the mole, 0.311 moles of potassium carbonate. That is how much potassium carbonate we started with. Step 3, as with every other stoichiometry problem, is the mole ratio. So 1 mole, as we look at our balanced equation, I have 2 potassiums, 1 carbonate, or 1 carbon, 3 oxygens from the carbonate, 3 oxygens, and 2 hydrogens, 2 chlorides, 2 chlorides. We're all completely balanced. But what I need to worry about here is 1 potassium carbonate to 2 moles of hydrochloric acid to 2 moles of potassium chloride to 1 mole of water to 2 moles of carbon dioxide. Now, what we need to focus on is potassium chloride because that is our other known value. We want to calculate the theoretical yield of potassium chloride in order to then find out what our actual or our percent yield actually happens to be. So we set up our mole ratio, we cross multiply, I get X would equal 2 times 0.331. This is where I worry about my mole ratio especially. But again, notice the same mole ratio that I have here, this mole ratio, is the one that I pull from my reaction. This mole ratio, this mole value right here is what I get from my actual amount that I have in this particular problem. So what I end up with is 0.662 moles of potassium chloride. Now my step 5 will be to, as with my other stoichiometry problems, to go from my moles back to the requested units, which in this case are grams. So I multiply my mole value of potassium chloride by the gram molar mass of potassium chloride. My mole values cancel out. I get 49.4 grams of potassium chloride. That is my theoretical yield. In a best case scenario, if I put in 45.8 grams of potassium carbonate, I should be getting out 49.4 grams of potassium chloride. Now, what does this actual problem say? It says I had 46.3 grams produced, which is a little bit less than my theoretical yield. Percent yield is the actual yield over the theoretical yield times 100. So in this case, my percent yield is 93.7%. So we're just, with percent yield, it's just one step beyond our original stoichiometry problem. That original stoichiometry problem would give me the theoretical yield, and then my actual yield I would have to be given in the problem in order to calculate a percent yield. Or if we did this in a lab, which we will do coming up, we would also have the same situation where we would have to calculate a theoretical yield and then compare that to our actual yield as over the course of the experiment. Now, one other concept in stoichiometry are limiting reagents and excess reagents. The limiting reagent, which is something on the left hand of a chemical equation, will restrict the amount of product that can be produced. We'll get some examples of this. It will run out in a chemical reaction. It will be the thing that runs out first. And if this particular reactant runs out, the reaction can't proceed anymore because you've ran out of that particular reactant. And therefore, your product will not be produced from that reagent anymore, or from that reactant anymore. The excess reactant is what you will still have left over after the limiting reactant is used up. It'll just be sitting there waiting for some other reaction to happen, but it can't react with the limiting reagent because that's already been used up. Okay, I see you have some more animations I need to fix, but this is a good example. Now, these are one of the mole problems. These are very, very hard to do in the real world because it's very hard to measure moles, but it gets us to focus on what the main idea here is, which the main idea here is not to worry about converting units to moles. Here we just look at the mole values as they stand. That eliminates one step of stoichiometry. So here, if 1.21 moles of zinc and 2.65 moles of hydrochloric acid react in a single replacement reaction, which reactant is in excess and by what amount? And if we change those mole values back to grams, we would be able to find out by what amount. Now, I particularly like gram measurements because that's something we can actually do. Liters of gas at STP or the grams of a substance are both very valuable in the real world. Now, this is saying calculate the theoretical yield of each product at STP. So in this case, just like in our previous stoichiometry problems, we will need to have a balanced reaction. Now, zinc and hydrochloric acid, single replacement reaction, you should be able to set that up. You would know that hydrogen and zinc, hydrogen is less active. Hydrogen here is the ion, zinc is more active. The rule is that the more active element will become the ion. So what actually happens is zinc will be oxidized, will become zinc with a 2+ charge. Hydrogen, which here has a +1 charge, you have 2 +1 charges. They will each gain an electron from zinc and become reduced into hydrogen gas, which will bubble out of your solution. That's a standard, typical single replacement reaction, which it's very good to be aware of. Now, step 2 in most cases would be to go from your units to moles. However, in this case, you don't have to worry about that because your units are the moles. Step 3, again, is your mole ratio. So for every mole of zinc, you're going to need 2 moles of hydrochloric acid, and we would produce 1 mole of hydrogen gas and 1 mole of zinc chloride, formula units. Of course, this would still be aqueous. It would be dissolved in water. But if we were able to evaporate off the water, we should get 1 mole of zinc chloride for every mole of zinc and every 2 moles of hydrochloric acid. But what we need to actually look at here is which reactant is in excess. So we can do that in a couple of different ways. This is different from other stoichiometric calculations. What I would say, this is a step 3A, you determine which reactant is in excess by calculating which would make more of your product. In this case, I have to move this a little bit. So in this particular case, if I reacted all of my zinc, I would produce, so I have 1.21 moles of zinc. The mole ratio is 1 zinc to 1 hydrogen gas. If I reacted all of my zinc, meaning my 1.21 moles of zinc, I would produce 1.21 moles of hydrogen gas. If, however, I reacted all of my hydrogen chloride, and the mole ratio there is 2 moles of hydrogen chloride to 1 mole of hydrogen gas. If I reacted all of my moles, I would end up with 1.32 moles of hydrogen gas. So either my zinc is going to run out first or my hydrogen chloride is going to run out first. Based on which one produces more product, in this case, my 2.65 moles of hydrogen chloride is going to produce more product. Well, that actually means that I'm going to run out of zinc because I would make less product. I'm going to run out of zinc before I run out of hydrochloric acid. So the reactant in excess is the one that would make more product. And then for my actual amount of hydrogen gas, for example, produced, I would have to base that on my smaller value, because what would happen if I had hydrochloric acid in excess, then the zinc is going to run out. So I have to base my actual yield on, or my theoretical yield on, the smaller quantity of reactant. In this case, the zinc will run out first because we just did the other calculation to determine that we would make more hydrogen with if all of the hydrochloric acid got used. However, we can't do that because we're restricted to this amount of zinc. We have 1.21 moles of zinc. That was our determination earlier. So what this tells us is that the zinc will run out before the hydrochloric acid does. Hydrochloric acid will be around longer. So from there, I would calculate, since zinc is my limiting reagent, I would do my mole ratio, which in my original formula back here was 1 zinc to 1 hydrogen gas to 1 zinc chloride. So I would compare zinc to zinc chloride, for example. I would get 1.21 moles of zinc, and then my X value in this case, I would make 1.21 moles of zinc chloride. I would also make 1.21 moles of hydrogen gas because I have 1.21 moles of zinc. It's a 1-to-1 ratio. I would make 1.21 moles of each of these products. The next thing you're supposed to do is change your moles to units. We're back to standard stoichiometry. These are our theoretical yields based on the amount of zinc that I have. I have hydrogen chloride or hydrochloric acid in excess. So if I'm dealing with an ionic compound, I can't do liters of gas at STP because this is an ionic compound. I could do grams. What would I produce from this particular reaction? If I evaporated off the water from my solution, I would get 165 grams of zinc chloride. And then if I were able to measure my hydrogen at STP, 1.21 moles of hydrogen gas times my conversion is 22.4 liters of any gas, not any substance, but any gas at STP. I would get 27.1 liters of hydrogen gas at STP. Now, the question of why it might be easier to measure gases as volumes at STP is because it's very hard to put gases on a scale and weigh them. So that is why we generally must remember this 22.4 liters, that is the space occupied by 1 mole of any gas at STP. Now, again, keep in mind, H2 is because hydrogen in nature occurs as a molecule. However, 1 mole of helium atoms would occupy the same volume because helium is not a diatomic element. One more challenge here with the limiting reagent would be to determine how much hydrogen chloride, or originally which became hydrochloric acid, remains. So we have a 1-to-2 ratio in our original equation was zinc and hydrochloric acid. So 1 mole of zinc to 2 moles of hydrochloric acid. We determined earlier, or we saw earlier, we had 2.65 moles of zinc. 2.65 moles of hydrochloric acid that were available. 1.21 moles of zinc, 2.65 moles of hydrochloric acid. That means with this ratio that we've set up, 1.21 moles of zinc were consumed, and that leaves us with, if I do my cross multiplication, 2.42 moles of hydrochloric acid was used up. How much is remaining from that? We began with the 2.65 moles, and I have 0.23 moles of hydrogen chloride or hydrochloric acid sitting around for a reaction to happen, but it can't react with anything because the zinc is gone. There's no more zinc. It's only zinc chloride and hydrogen gas as products. And if I wanted to change that back into grams, again, 0.23 moles times the gram molar mass of hydrogen chloride would give me 8.4 grams of excess hydrogen chloride or hydrochloric acid. Very soon we'll be talking about molarity, which is where you'll be much more aware of the mole values of acids in a solution. And from here, I will put up one more limiting reactant problem for you to practice. In the meantime, I think this is a good introduction into limiting reagent.